Hi everyone, welcome to your lesson as part of week 5 of your online learning for higher chemistry. So today we are continuing our revision of Unit 1. Last week we were focusing on periodicity and structure and bonding in elements. So we're continuing on with that today by looking at structure and bonding in compounds. Okay, so in the video we'll go through the key learning from this topic, which was part of Unit 1, Chemical Changes in Structure. You should have notes in your notes jotter that you can refer back to, but it's also useful to have your Unit 1 booklet handy, so you've got your learning outcomes and summary notes there, as well as practice and exam questions, which you might want to work on as part of your revision later on in the lesson time. So same as last week, this is content that we've covered before. There's nothing new here, so there's no need for you to write any notes. If you want, you can just watch the video and just recap on the topics, the main content. If you feel it helps, then feel free to make some notes, but it is absolutely not required. Okay, you can refer back to the booklet and to the notes that you already have in your notes jotter. Okay, so as I said, this is continuing on from our work on the bonding in elements last week, and as part of that we took a look back at some of our common bonding types. So we saw covalent bonding as part of covalent molecular and covalent network elements, also the difference between those structure types and how that affects the properties of the substance. We also had a look at metallic bonding and the monatomic structure that the noble gases have. So for elements, monatomic and metallic bonding are only found in elements, so you won't find any compounds that have those sorts of structures. The covalent molecular and covalent network types are found in elements and compounds, so you'll be seeing those again today. And as well as those types, in compounds we have a third bonding and structure type possible, which is ionic bonding. Okay, so we should be familiar from Nat 5 and from the elements topic with some of the properties, a kind of general structure of these different types. But as always, or as often with higher chemistry, this topic is building on what we already know from Nat 5. So one of the first things we would have looked at in this topic is something that we call the bonding continuum. So at Nat 5, you would have thought about bonding and structure types as being very separate categories, and they are to an extent, but what we actually find is bonding is much more fluid. The different bonding types exist on what we call a continuum or a spectrum of different types of bonds, and this can largely be predicted by thinking about the electronegativity values of the elements, the atoms that are making the bond. Okay, so electronegativity, we took a look back at this in the periodicity recap last week. It is the attraction that an atom has for bonding electrons. So with elements, we were looking at atoms of the same element forming bonds, so they would have the same attraction, the same electronegativity values. But when we look at compounds, those values will quite often be different, which is why we get different bonding and structure types appearing with compounds. Okay, so thinking about our covalent and ionic bonds. Covalent bonding can actually be divided into two categories, and all of this is based on the difference of electronegativity. So if we have a look at the continuum, we can see all three bonding types that we can find in compounds. So over at the left hand side of the continuum, you've got what we call nonpolar covalent bonds, sometimes called pure covalent, then polar covalent, and then finally the ionic bonding. And as I said, this is all based on electronegativity difference. So starting at the left of the continuum, the nonpolar bonds are the type that we would find in elements. That's the type of covalent bond that forms when both atoms have the same electronegativity. So when there's no difference in electronegativity, that means both atoms are attracting the bonding electrons equally, and therefore the bonding electrons are shared equally between them. So that's our kind of traditional picture of a covalent bond, with those two electrons being shared between the two atoms. What we find is some combinations of different elements can have the same electronegativity. So you might have a compound where there are pure non-polar covalent bonds, but more often it's found in elements. Usually in a compound we'll be combining atoms that have different electronegativities, and that brings us on to our second type of bond. Okay, so your polar covalent bond forms when there's a small difference in electronegativity between the two atoms. So what this results in is one atom will have a higher electronegativity. That means it attracts the bonding electrons more strongly. So those electrons are no longer being equally shared between the two atoms. And what is formed is something we call a permanent dipole. So that's a difference in charge, positive, negative. We end up with one atom of our bond having a slightly positive charge. That's the one with the lower electronegativity that's had the electrons pulled away from it. So it's got less of a share of the negative electrons, which is why it ends up slightly positive. And the atom with the higher electronegativity, because it has more of a share of the negative electrons, ends up with a slightly negative charge. These symbols, so delta plus and delta minus, you'll see those, you should be used to seeing those symbols to denote a dipole. You'll see them used in diagrams like this one here. So this example has got hydrogen and iodine forming a bond. Iodine's got a higher electronegativity, so it's pulled the electrons closer to itself and has a slightly negative charge. The hydrogen is left with less of a share of the electrons and therefore has a slightly positive charge. Okay, and the final bonding type is ionic. So this is an extreme version of a polar covalent bond. This type of bond forms when the difference in electronegativity is large, and it's so large that one atom basically pulls the bonding electrons away from the other. So rather than them being shared between them or even shared unequally, the atom with the higher electronegativity just pulls the bonding electrons away from the other one. That means we form ions. So instead of those slight positive and negative charges, we get full positive and negative charges, and ions are created. So in the example here, you've got cesium fluoride. Fluorine has a higher electronegativity, so it's pulled the electrons away from the cesium and formed a negative ion, and cesium has formed a positive ion. Okay, so looking at electronegativity tells us a lot about the type of bond that forms, but it's not the only thing that determines the type of bonding. And one thing we have to be careful with is that we don't ignore other evidence that we might have. So if we know information about the properties of a substance, things like whether it conducts electricity, the melting and boiling points, these are also things that we should take into account when we're thinking about the kind of bond that a substance, a compound will contain. Okay, so there are exceptions to the kind of bonding rules that we're used to, particularly when you think about ionic bonds at Nat5, and mostly at higher, we see them with metals and non-metals, those types of compounds, because there is quite a big electronegativity difference between metal and non-metal elements in general. But there are some exceptions, and you might see examples where the properties would actually show us, although we have a metal and a non-metal in a compound, actually it might be a polar covalent bond instead of ionic. So just something to watch out for, that we don't ignore other evidence that we might have. Okay, and something which is quite an important part of the bonding in compounds topic is looking at the properties that a substance has and being able to link them to the type of bonding, being able to explain why a substance has those particular properties. Okay, so now we know how to predict the type of bond that forms between two atoms. We are going to forget about ionic bonding for the most part. In the bonding in compounds topic, we will mostly have to think about substances which are covalent polar covalent or non-polar covalent. And the next bit of the topic is particularly focusing in on that. So although we can think about electronegativities to look at the type of bond that forms between atoms, we also have to consider the overall molecule that those atoms are found within. Because what we find with the shape of certain molecules is that can affect the polarity of the bonds. So as part of working out if a substance is polar or non-polar, we need to consider the type of bonds, whether the bonds are polar or non-polar, but we also need to look at whether the arrangement of the bonds in the molecule allows it to be polar or non-polar. So this we'll look at each category individually. If we start by looking at non-polar molecules, the kind of obvious, hopefully, situation where a molecule will be non-polar is when it only contains non-polar bonds. So if you only have atoms with the same electronegativity joining together, you only have non-polar bonds, then there's no way that your molecule can be anything other than non-polar. Okay, so kinds of molecules to watch out for here are obviously our elements, which will have the same electronegativity and therefore non-polar bonds, or compounds where you have atoms of the same electronegativity joined together. One example just to be aware of is bonds between carbon and hydrogen. So these elements do have a slight electronegativity difference, but it's so small that the bond between carbon and hydrogen is considered non-polar. So if you see CH bonds in a molecule, then remember they are non-polar bonds, although you wouldn't expect that necessarily from the electronegativities. Okay, so that's the easy non-polar situation. The slightly trickier one is if you have a molecule where there are polar bonds, so you do have a difference of electronegativity between the atoms, but the shape of the molecule is such that those bonds cancel each other out. And what we're really looking for here is the shape to be symmetrical. So we're looking for lines of symmetry in the molecule, and that allows the dipoles, the positive negative charges, to cancel each other out. Okay, now this seems like it's quite tricky, but really you're just watching out for similar molecules, similar shapes of molecules that allow this symmetrical cancelling out situation. So there's a few examples here. If you see a molecule that's linear with more than one bond, so carbon dioxide's a really common example of a non-polar molecule. Because of, you can see there's a line of symmetry right down the middle here with carbon. It's exactly symmetrical on either side. That shape allows the polarity of those bonds to cancel out, even though there is an electronegativity difference, and carbon dioxide is non-polar overall. Okay, so watch out for that example. Also, tetrahedral molecules, so the four bonds shape that we know from Nat5. If you have a tetrahedral molecule with 4 identical bonds, then again that's a symmetrical shape. You can kind of think of it like the negative charge in this case, the slightly negative, is kind of spreading out equally in all directions from the carbon. So that is another symmetrical shape that allows the dipoles to cancel. So they're the kind of common ones that you'll see for non-polar molecules where they have polar bonds but they cancel out. Okay, so then if you have a molecule that has polar bonds but it's not symmetrically arranged, it doesn't have that kind of shape that allows the bonds to cancel out, then that is a situation where your molecule will be polar overall. So again, you're watching out for typical kinds of shapes here. The linear shape, again, can result in polar molecules if you've got just the one bond. So the carbon dioxide linear shape has 2 bonds going out in either direction from the carbon. This linear shape is just one bond. So your diatomic kind of shape, you can see the negative is only going in one direction here. There's only one bond. There's nothing to cancel that out. Water, so the angular shape, you should hopefully be familiar with water being polar. Again, because it's not linear, because it's not a straight molecule like carbon dioxide is linear, so it cancels out, but the angular shape of water means that the charge, you can see the negative charge is all going up. So there's no cancelling, there's no balancing out of the charge. Pyramidal shape, trigonal pyramidal, ammonia is the common example there that you'll see. Again, similar to water except you've got a third bond. All the charge is going up in the one direction. And although we mentioned tetrahedral before, if you have a tetrahedral molecule where there's different bonds, so in the last one, all 4 of the bonds were chlorines, and that allowed the polarities to cancel out because you had that balanced charge in all directions. Here, we've got this carbon-hydrogen bond at the top, which is non-polar. So that one difference, that one non-polar bond, means you have no cancelling of these polar bonds down at the bottom. So be careful with tetrahedral and linear shapes. Make sure you know the difference between linear versus the carbon dioxide form of linear. Tetrahedral, it is important to look at what bonds you have, what atoms are attached. The angular and the pyramidal shapes are definitely polar. If you see them with polar bonds, then you know that's the case, but you just have to be careful with the other 2. Okay, so we're now going to start thinking about properties that compounds have. So knowing about the bonding type is obviously important, but what we have to consider is the bigger picture of what's happening inside that substance. And if we're talking about a molecular substance, which we quite often are when we're dealing with compounds, we know already from the elements topic that bonds are not the only attractive force that exists. There are intermolecular forces between molecules, and quite often those are the forces If we're talking about molecules, those are the forces that need to be broken when we think about things like melting and boiling, and they're the important forces for us to consider. So when we look at intermolecular forces, just before we get into the different types, the reason we know these forces exist is because of the noble gases. So we know the noble gases are monatomic, they don't have any bonds between the atoms, but they are still able to turn into liquids, so to condense, and then to turn into solids, to freeze. If you take them to low enough temperatures, you can get them to change into those states. And what they're doing when they change into those different states is the atoms are coming from being a gas very far apart to moving closer and closer together. And the only way that they would be able to come close together and form this kind of structure of a solid that's very organised is if there was some kind of force between the atoms attracting them together. And we know that's not bonds because we know they don't form bonds. So that is our evidence that, well, there must be some other force attracting the atoms together. And this is how we know that intermolecular forces must exist. And we know that as well as existing in the noble gases, they also are found in molecular substances. Okay, so there's three main types of intermolecular forces. When we looked at elements, there's only one type of force that you find in molecular elements, so we will only consider that one, but there's two other types that are found in compounds. So the one we should be fairly familiar with from looking at elements is LDFs, London dispersion forces. So these are our weakest type of intermolecular force. They are found between all atoms and all molecules. When we think about what creates them, you can see why. But even though they're there between all atoms and all molecules, we only really talk about them if they're the strongest force that's there. So when we look at the other forces, a molecular substance might have a stronger intermolecular force, so that one kind of becomes significant. That one is the one that we talk about when we think about the influence on its properties. The LDFs are still there, they're always there, but we only talk about them if they're the strongest force, because that's when they actually are significant and having an effect on the properties. Okay, so the reason why all atoms and molecules have LDFs between them is because they're caused by the movement of electrons. So you've always got electrons in atoms, therefore you've always got LDFs between them. And what happens is electrons are randomly moving around in atoms all the time, and sometimes that means temporarily, for a fleeting moment in time, all the electrons might be at one side of an atom, and then they might be all at one side, another side, and then up at the top and then down at the bottom. So you get these areas created in the atom where there's a slightly negative charge because all the electrons are over there. But then you also get, as a result of that, you would get the other side ending up slightly positive because there's no electrons over here. So we've got what we saw with polar bonds. We've got a dipole created, a difference between charges, positive, negative, slightly negative. But these are what we call temporary dipoles because they only exist for instants of time before the electrons are moving again. What also happens if you have one atom and all the electrons go to one side, then the neighbouring atom, its electrons would jump away from that negative charge. So that creates what we call an induced dipole. So in the next atom, a dipole is created because of the electrons in the neighbouring atom. So essentially, the electrons moving creates these temporary and induced dipoles, and then between different atoms, those dipoles attract each other. So if we've got an atom here, there's a slightly negative charge over at this side, that is attracting the slightly positive charge on this neighbouring atom, and that dotted line is what we call a London dispersion force. That's the force of attraction. Okay, and because these are caused by the movement of electrons, then as you get more electrons in your atom or in your molecule, or as the mass of your molecule increases, sometimes described that way, the more electrons you have, the stronger these forces get. So that can be important if you're considering two substances that only have LDFs, there's no stronger forces, but there's a difference in their melting points, then we would look at, well, how many electrons do they have? Because the one with more electrons would have stronger LDFs. Okay, and that's something we saw in the elements recap when we're thinking about things like how the boiling points of the noble gases increase down the groups because there's more electrons and there's stronger LDFs. We also see that effect in nonpolar compounds. So in a nonpolar compound, all you would have, same as with an element, all you would have is LDFs between the molecules. That's the strongest force that's present. Okay, so moving on. If you have, can't quite see that. If you have permanent dipoles, so if you have polar bonds, essentially, if you have a polar molecule, then that allows you to form this second type of intermolecular force, which is stronger, and it's called permanent dipole interactions, or PD for short. So these are stronger than LDFs, but they're not the strongest force. Hydrogen bonding is stronger. They are attractions between permanent dipoles in polar molecules. So you do not find these in non-polar substances. You only find it in polar substances. Remember what we said earlier, that a polar bond is what we call a permanent dipole. So that difference of electronegativity, slightly positive, slightly negative, is a permanent dipole. And what basically happens is, if you have a polar bond within your molecule, you've got that dipole, slightly negative, slightly positive, then the slightly positive of this atom will attract the slightly negative of a neighbouring molecule. So there, between the permanent dipoles of different molecules, you have this interaction or attraction occurring. Okay, so majority of the time, if you have a polar molecule, this will be the stronger force, so permanent dipoles, unless it's able to form a stronger version of permanent dipoles, which is the final force that we call hydrogen bonding. Okay, so with hydrogen bonding, although it's called bonding, remember it's still an intermolecular force. It's not a bond like a covalent bond is. This is our strongest type of intermolecular force out of LDFs and PD, but it is still weaker than a bond. So bear that in mind. It's nowhere near that same strength, even though it is the strongest intermolecular force. Hydrogen bonding is a specific type of PD attraction which forms between molecules that have specific bonds. So your molecule has to contain a hydrogen joined to either a nitrogen, an oxygen, or a fluorine atom. If it does not have that specific kind of bond, it will only have PD if it's a polar molecule. But if it does have those specific bonds, then you get this stronger type of PD interaction called hydrogen bonding forming. And that would then overtake the PD, so hydrogen bonding would be the force that you would be talking about when you think about the properties of that substance. Okay, so common example is water. So in water you've got oxygen, the red atom here, joined to hydrogen, and then another one. So between water molecules, you have hydrogen bonding existing. The intermolecular force, that attraction between the permanent dipoles of the different molecules. Okay, so just while we're talking about water and hydrogen bonding, this intermolecular force does have quite a significant effect on the properties of water, and it is something you should be aware of. So one of the things that hydrogen bonding causes is the boiling point of water to be higher than expected. So based on similar molecules where you've got similar oxides, a non-metal joined to oxygen, the boiling point of water should actually be a lot lower, should actually be a gas at room temperature. But hydrogen bonding, because it's such a strong force that exists between the molecules, it needs a lot more energy to break, then that raises the boiling point of water much higher and means it's a liquid at room temperature rather than being a gas. Okay, so that is one big impact. The other impact is when we think about ice, so kind of the opposite side. The hydrogen bonding in ice, so between water but when it's freezing, means that the water molecules don't have to pack as closely together as they do in normal or other solids. So if you think back to the picture we saw a few slides ago of solid, liquid, gas, in a solid you've got your atoms all tightly packed together, nice neat rows. That doesn't happen in ice. There's gaps between the molecules, more so than in other solids, so they don't have to pack as closely together. And what that means is the density of ice, the solid form of water, is a lot lower than what we would expect it to be, and it actually means that it's less dense than water. So the whole reason why ice is able to float on top of water is because of hydrogen bonding. And if that hydrogen bonding didn't exist, the ice would be more dense and it would sink. Okay, so we've had a wee look at some properties of water and how they're affected by the intermolecular forces, by the hydrogen bonding. This is something which more generally we can look at for other substances, not just water. So something you should be able to do, you should be able to explain as part of the higher course, is the properties that a substance has. So based on its bonding and structure type, based on the intermolecular forces that it contains and the strength of those forces, you should be able to explain or predict the properties of that substance. Or maybe compare two different substances, two different compounds based on their properties. So there's a few different properties we should be able to do this for. The first of which is melting and boiling points. So this is mostly based on the polarity of your substance. You don't really get asked this for ionic substances. They have high melting and boiling points anyway. What you'll get asked about is to compare different molecular substances. So if you have a polar substance with polar molecules, they generally have higher melting and boiling points than non-polar substances, provided you're comparing substances that are similar mass, similar size, similar number of electrons. So remember, that would mean that their LDFs are similar in strength. So then if they've got similar LDFs, but there's a big difference in the melting and boiling points, it must be because there's some other intermolecular force involved that would cause that difference. So when we look at those melting and boiling points for a molecular substance, those are determined by the intermolecular forces between the molecules. That's what you're breaking when you melt or boil the substance. So if you've got a polar substance, then it will have PD-PD interactions or possibly hydrogen bonding, whereas your non-polar substance will only have LDFs, and because your LDFs are weaker, then they're easier to break, and that gives you a lower melting and boiling point. So in questions to do with explaining melting and boiling points or comparing them, you want to think about mentioning the polarity of the substance. Is it a polar or non-polar substance? What kind of forces it has, so what's the strongest intermolecular force? Is it LDFs? Is it PD-PD? And then you can link that to the difference in the melting and boiling points based on the strength of the intermolecular forces. Okay. So as I said, polar and non-polar are your two kind of categories for this, but bear in mind that polar molecules with hydrogen bonding have even higher melting and boiling points. So we see this, we talked about water already having a higher boiling point than expected. Other molecules like ammonia and hydrogen fluoride have that same kind of impact, so they all have higher boiling points than they should based on similar molecules because of the hydrogen bonding between them. Okay, so if you're asked in an explain question about melting and boiling points, think about polarity, intermolecular force, and then linking that to the difference between the melting and boiling points, or explaining whether it's a high or low. Okay, moving on to solubility. This one is something you might remember being taught a little phrase about, which is like dissolves like. So basically, when we look at solubility, or sometimes called miscibility, when you think about mixing two liquids, solubility is generally dissolving a solid in a liquid. Similar words, they essentially mean the same thing. They're just describing different types of substances. What this is down to, so like dissolves like means if you have the same kinds of substances, then they will mix together or they will be soluble. And if they're not similar, then they won't. And that similarity is down to looking at the polarity of the substances involved and looking at the strength of the intermolecular forces that they can form. Okay, so if we think about polar substances, and ionic substances also come into this category because they're just an extreme version of polar. Those sorts of substances would be soluble in a polar solvent, and water is your most common polar solvent. Whereas if we try to dissolve it in a non-polar solvent, so something like hexane, they would be insoluble. And the reason is because with the polar solvents, if you've got a polar substance, PD-PD attractions or maybe hydrogen bonding, water has got hydrogen bonding between the molecules. If you mix those two substances together, they can both form forces that are similar strength. So the forces between the separate substances can break between their molecules, and then the molecules can mix with each other and form new forces. So because they have similar strength of forces, that's what allows them to mix. But if you tried to do this with a non-polar substance, so if you put a polar and a non-polar substance together, the non-polar substance can't form strong enough forces to mix with the polar substance. So they would stay separate. So that's the sort of thing you see with oil and water, where you see them form two separate layers. They don't mix together because oil is non-polar and water is polar. Okay, so the little example here is showing you ethanol, the alcohol, which has got this OH bond, so it can form hydrogen bonds. Water, we know, can form hydrogen bonds, so the two of them can form the bonds to hydrogen bonds, intermolecular forces to each other, which allows them to mix together. Okay, similar idea but opposite. If we think about non-polar substances, so if you have something that's non-polar, it'll be soluble in a non-polar solvent like hexane, or another one here, dichloromethane, and will not be soluble in a polar solvent. So a non-polar substance would not dissolve in water. That's again because of the strength of the forces involved. So because one will only have weak LDFs, the other will have much stronger forces like hydrogen bonds, then they will not mix together because the hydrogen bonds wouldn't break if they can't form a similar strength of force when they mix together. Okay, so remember your phrase like dissolves like. If you have to describe or explain solubility, you want to identify the polarity of the solvent, whether it's polar or non-polar, identify the polarity of the substance you're trying to dissolve, and if they're the same, then it's going to be like dissolves like, and just identifying what intermolecular forces are involved in order for you to explain that. Okay, solubility and melting boiling points are the main ones you get asked to explain, but there's a couple of other properties just to be aware of, more often appearing in things like multiple choice questions. So one of which is viscosity. So this is a property that measures the thickness of a liquid, how easily it flows, whether it's runny or whether it's really thick and gloopy. So sometimes you'll see experiments to do with viscosity. So you might see this sort of setup here where you've got tubes or burettes with different liquids, and they'll pass a ball bearing or a marble or something down each tube, and they basically measure how long it takes for the marble to reach the bottom of the tube, so how long it takes for it to fall through the liquid. And the longer it takes, the more viscous your liquid is. So if you think about, trying to drop a marble through water, will be fairly easy. It's going to fall through the water, to the bottom of the glass quite quickly. But if you try and do that with a glass of treacle, then it's going to take a bit longer to get to the bottom. Okay, so this sort of experiment is something you should recognise. There's not a huge amount to explain to do with viscosity, but something to watch out for is that it's very much affected by hydrogen bonding. So the more hydrogen bonding you have between molecules, the more viscous they'll be. So if you look at some alcohols here, you've got one hydroxyl group. This diol has got two hydroxyl groups, and then triol, this is glycerol, with three hydroxyl groups. The more hydroxyl groups allows for more hydrogen bonding between the molecules, and therefore the glycerol here at the end will be much more viscous than ethanol because the glycerol's got more hydrogen bonding. Okay, so watch out for viscosity, and then the other one just to be aware of is the attraction that a liquid has to a charged rod. So if you have, this is a straight cut polar non-polar situation. If you have a polar liquid, then it will be attracted to a charged rod. So basically if you have, a plastic rod, charge it up with a cloth, just get some static electricity built up, and then hold it next to the flow of water so you can see the stream of water or the stream of liquid coming out of the burettes here. If you have a polar liquid, then the liquid will bend towards the charged rod, so it will be attracted to it, whereas a non-polar liquid will just pass by with no effect. So the polar liquid is being attracted to the charged rod because the polar liquid's got permanent dipoles in it, so it's got those charges, and obviously the static electricity in the rod does as well. Okay, again, this is the kind of thing you might see this experiment shown to you or something similar, or perhaps in a multiple choice kind of question. Okay, so that's us covered the main points of the bonding and structure in compounds topic. So hopefully you've remembered quite a lot of that from watching the video. If there's anything you want a bit more explanation, a bit more detail on, as I said at the start of the video, go to your Unit 1 booklet or go to your notes, and you'll find a bit more detail there. What you should do, just to kind of self-assess how well you feel about the topic, is if you go to your Unit 1 booklet and take a look at the learning outcomes for the structure and bonding topic, just have a look through them and see how well you think you know that outcome, or you'd be able to explain that. And that once you've done that, you will maybe identify some areas within the topic that you need a little bit more practice with. So you will hopefully have a little bit of time for some personal revision of this content. So in the lesson instructions video and slides, there's some suggested activities that you might want to try. Part 2 of our work today, or lesson 2, is going to involve a live tutorial. So at the end of the block today, we're going to do a live tutorial, and in that tutorial we're going to go over the answers to the worksheet that you've been asked to complete. So once you've done a little bit of personal revision, make sure you leave yourself time to complete the worksheet. So maybe even try it first if you think you might run out of time. The worksheet has got questions on this compounds topic, but also a little bit to do with periodicity and elements. So just a real test of what we've done over the last few lessons. Have a go at all the questions, take a note of your answers, and then at the live tutorial we'll go through the answers, and particularly focusing on written questions where you've got to do some explaining to do with this topic, because that's one of the trickier parts of Unit 1, is all these kind of explanation questions that you can get. Okay, so good luck with your revision and the worksheet, and myself or Mr. Shepherd will see you later on today for the live tutorial. Bye!